Hello, so in this video we're going to talk through Theme 5 homework, which is all to do with hypothesis testing and confidence intervals. So, question 1. Marks on a test are known to be normally distributed. So first things first, I'm actually just going to write this down. So X I'm going to represent as the mark on a test. Okay, so it's always good to define what your random variable is. So in this case, I'm letting X represent the mark on a test. Okay, they're known to be normally distributed, and previous evidence has shown that population standard deviation of the marks is 4. Okay, so in other words, I know that the population standard deviation is equal to 4. Okay, 60 test papers are selected at random, so n equals 60. And the mean weight of these, or the mean mark of these 60 test papers, are found to have a mean of 30. Okay, so X bar, the sample mean, is equal to 30. We're asked to construct a symmetric 95% confidence interval. There's a mistake here. So for the population mean weight of the chocolate bars, obviously I've just copied and pasted this question. I haven't changed the fact that it's not chocolate bars, it's the marks on a test. So what I mean here is construct a 95% confidence interval for the population mean mark of the test papers. Okay, so ignore the fact it says mean weight of the chocolate bars. Okay, think about it as a mean mark instead. Okay, cool. So first things first, I need to figure out what type of distribution I should sample from. Should it be a t distribution or should it be a z distribution? Because those are the only two distributions we use in this course. So remember, I asked myself 2 questions. Number 1, I asked myself the question, have I got a sample size greater than or equal to 30? Okay, so that's the first question I ask. The second question I ask myself is, do I know the population standard deviation? Okay, now if the answer to any of these questions is no, okay, so if the answer to the first question, if the sample size is not greater than or equal to 30, or if I don't know the population standard deviation, then I know I should be using a t distribution. Okay, if the answer to both of those questions are yes, then I know I can use a z distribution. So let's test it out. Okay, do I have a sample size greater than or equal to 30? Okay, so the first question, do I have a sample size greater than or equal to 30? Yes, I do. I have 60 test papers. Okay, so the answer to that question is yes. Okay. Next question, do I know what the population standard deviation is? Well, yes, I do. I've been told that previous evidence has shown the population standard deviation to be 4. Okay, so I know what that is. So therefore, the answer to that question is also yes. Therefore, I know I'm going to be sampling from a z distribution here. Okay, so always ask yourself the question, is it a t distribution? Okay, is it a z distribution? In this case, the answer to both those questions is yes, therefore I can use a z distribution. All right, cool. So I need to construct a 95% confidence interval for the population mean weight. So remember, what I'm saying here is, look, I've gone out, I've collected 60 test papers, and I've found that they have a mean weight of 30. Okay, now I need to figure out what's the upper bound and what's the lower bound for these papers. Okay, so I need to work out the kind of bounds, if you like, which can contain 95% of my data. Therefore, I am 95% confident then that I've captured the true population mean mark. Okay, so here's how I'm going to do it. Okay, first of all, I'm going to say, look, in the middle, I have got my true population mean mark. Okay, which I'm going to call mu. Okay. And then I basically say, look, if I take away some margin of error from my sample mean mark, okay, that should be my lower bound. And my upper bound should be if I add on that same margin of error, because it's got to be symmetric, so I've got to add and subtract the same margin of error each time from my sample mean mark. Okay, so I've got my sample mean, that's equal to 30, okay, and then basically I'm going to add and subtract some margin of error to basically allow give a little bit of allowance in order to capture what the true population mean mark should be. So in other words, this down here is going to be taking away m, and this up here is going to be adding on that margin of error. Okay, so the next question is, well, okay, what is that margin of error? Well, it's given in terms of units of standard deviation. Okay, so in this case, m will be equal to, well, let's have a think. So m is going to be equal to, first of all, I need to work out how many units of standard deviation do I need to include in order to have 95% of my data included. Okay, so I need to look at that. So I'm going to basically look on my z tables, and I'm going to find the sort of units of standard deviation each side of the mean, which is going to include 95% of my data. okay? Then I need to multiply that by, if you like, my actual value of my standard deviation. Now, in this case, I don't call it standard deviation, I call it standard error instead, okay? But the standard error is going to be given by sigma over the root of n, okay? So this thing here is a bit like my standard deviation, but I call it standard error because it's, if you like, giving me some error each side of my sample mean in order to include my population standard deviation, or to find my population standard deviation. So, okay, let's actually go through and calculate each of these things. Well, this thing here is actually very, very simple to calculate, the standard error, okay? Because it's just simply going to be, well, sigma is equal to 4, and the square root of n, well, the square root of my sample size is 60, okay? Next thing, I need to actually calculate how many units of standard deviation each side of the mean will include 95% of my data. Well, if I just draw a very quick normal curve, okay, I know that I've got some population mean in the middle. Well, in this case, I'm actually going to put my sample mean instead, okay? And then I basically need to include 95% of my data, and it's got to be symmetric, okay? So that region there has got to be 95% in total, which means I've got 5% left over at each end. In other words, 5% of data I'm not included, and it's split over these two regions on the left and the right, which I've shaded in green. So if I split that 5% equally, I get 2.5% down here, and I get 2.5% up here, okay? So in other words, I need to find what value, okay, so what are the values which include 95% of my data. Well, the way which I could do that is say, well, okay, the probability that z is less than something, okay, and that something is what I'm after there, okay, should be equal to 2.5%. So I can jump over to my z curves, and I can find, okay, what value includes 2.5% of my data on the left. If I wanted to do it on the right, of course, I'd be looking at 97.5% of my data, because of course it's cumulative. But let's look at 2.5% of my data. Okay, so let's jump over to my curves, and let's find on my z curves 2.5% of my data. So I need to be looking in this region of my tables, and I'm looking for as close as possible to 2.5%. So 2.5%, remember, is equal to 0.0250. Okay, so I'm trying to find a value as close as possible to that. So let's have a quick peep. There we go. It's bang on. Now, of course, if I couldn't find it bang on, I would just find the next closest one rather than kind of interpretate values in between. But I found it exactly in this case. So that's going to be negative 1.96. So in other words, 1.96 units of standard deviation. Sorry, that's the wrong way. 1.96 units of standard deviation will give me 95% of my data being included. So it'd be negative 1.96 down here, and positive 1.96 up here. Okay, that's going to include 95% of my data. So therefore my value here, if you like, is going to be 1.96 units of standard deviation multiplied by my standard deviation. In here, I mean standard error, because it's calculating the error from the sample mean to include my true population mean. So let's actually find the value of m then. So if I stick the 1.96 times by 4 over root of 60 in my calculator, 1.96 times by 4 over the square root of 60. Let's have a look at that. So that's going to be 1.01, okay? So that's how much to add and subtract from my sample mean in order to include 95% of my data and capture the true population mean. So if I use this inequality then and say, okay, the lower bound is going to be x bar, which is 30, take away my margin of error, which I've just calculated as 1.01, okay? And then my upper bound, so mu can lie anyway up to 30 plus 1.01. So if I actually just calculate those values, my lower bound, my lower threshold, if you like, is 28.99. And my upper threshold for my true population mean is 31.01. So what I'm basically saying is that if I'm including, given this sample data, so 60 test papers found to have a mean of 30, and I know the true population mean is 6, sorry, the true population standard deviation is 4, okay, I know that if I want to include 95% of my data, I want to be 95% confident I've captured my true population mean. My true population mean should lie between 28.99 and 31.01. So it should lie in the sort of 29, 31-ish range, okay? So there is my final answer. Okay, good. All right, fine. Let's have a look at question 2 then. So question 2 says that a chocolate bar manufacturer is redeveloping their recipe. A test batch considering 25 new chocolate bars is found to have a mean weight of 100 grams and a standard deviation of 4. Construct a 95% confidence interval for the true population mean weight. Okay, so let's write this down, okay? So I've basically got a test batch consisting of 25 new chocolate bars. That's my sample size, okay? That's my sample data size, okay? So 25 chocolate bars. They're found to have a mean weight, and of course that's sample mean weight of these 25 chocolate bars. Look at the wording. A test batch consisting of 25 chocolate bars is found to have. In other words, now I'm talking about the sample mean, okay? And therefore the sample standard deviation as well. So the sample mean, x bar, is equal to 100. And the sample standard deviation, remember I'm not told, the wording of the last question, it was clear that it was population standard deviation. Here in this case, I'm talking about the standard deviation of the 25 chocolate bars, therefore it's sample standard deviation. So therefore I'm going to write S for sample standard deviation, okay? And that's equal to 4. Just remember our notation, okay? If we're talking about mean, okay, if it's sample mean, I use x bar or y bar or whatever letter I'm denoting to be my random variable, okay? If I'm talking about population, okay, I use the Greek letter mu, Greek letter for m, okay? If I'm talking about standard deviation, the sample standard deviation I represent as S for standard deviation, okay, spread. And if I'm talking about population standard deviation, I use the Greek letter S, which of course is sigma, okay? So just be very, very careful about what notation you are using. Okay, so in this case it's sample standard deviation, so therefore I'm using S, okay, and sample mean, therefore I'm using x bar. Now I've been tasked to find a 95% confidence interval, symmetric around the mean, for the true population mean weight, okay. So first of all, I need to figure out exactly what type of distribution I need to be using to find my critical values, okay. So I need to ask myself the same two questions as before. So, okay, if we have a look at this then, it's just hiding behind me, okay, if I have a look at this over here, the two questions I need to ask is, first of all, is my sample size greater than or equal to 30? Then I need to ask the question, do I know my population standard deviation? Noticing I'm using sigma there, because population standard deviation. So let's have a think. Well, first of all, do I have a sample size greater than or equal to 30? Well, no, I don't, it's 25. Therefore, I know I'm going to be using the t distribution there. Okay, but even so, I didn't know my population standard deviation anyway, so therefore I still would have used the t distribution. Okay, so I know that I'm going to be using the t distribution to find my critical values. Okay, so let's have a look at this. All right, so I first of all need to say, well, look, I'm looking for my confidence interval as being x bar minus some margin of error. That's my lower threshold, and x bar plus some margin of error. That's my upper threshold. Okay, where m in this case is going to be given as, well, I need to use my t distribution, and I'm looking for 95% confidence interval. So in other words, I need to look at the number of standard deviations each side of the mean, which will include 95% of my data. Okay. Then I need to multiply that by my standard error, which is sigma over root of n. In this case, I don't know sigma, so it's fine just to use my sample standard deviation instead. Okay. So remember that there are different ways of working out whether to have a t distribution or z distribution. This is by far the simplest way. There are different justifications you can make. This is by far the simplest method you can use, and I recommend that you use it in this course, okay? So this is how we work out whether we're using z distribution or t distribution in this course. Just ask ourselves these two questions. All right, cool. So let's actually calculate what m is equal to. So m is going to be equal to, first of all, I need to work out how many units of standard deviation I need to include in order to have 95% of my data included, okay? Well, fortunately and handily, with the t distribution, it's much easier to do than with the z distribution, okay? So if I come down here onto my tables, okay, if you scroll down into your tables, okay, so you will have these tables in an exam, if you scroll down to your tables, below the z tables, you find the t tables there, okay? Now, just have a look here, just have a look. With the t tables, they work slightly differently. First of all, you have the tail probabilities along the top, okay? So whereas with the z tables, you have kind of the row and the column, and that corresponds to your units of standard deviation from the mean. Here it's slightly different. Here you're given as the probability along the top and also a probability along the bottom, except the probability along the bottom is a confidence level, okay? But these probabilities basically either correspond to significance level or confidence level, okay? And then this in here is not the probabilities anymore, it's the units of standard deviation. So if you like, it's a bit backwards to how you use the Z tables. With the Z tables, you had your probabilities in here and then your units of standard deviation as the rows and columns, okay? With your Z tables, slightly different setup, you have your probabilities along the top and bottom, and then you have your units of standard deviation in the center, okay? So just be aware that it's slightly backwards. So in this case, I'm looking for a 95% confidence level. So I could use an upper tail probability of 2.5%, because of course those two tails get 5% split among them, so it's 2.5% each, okay? Or I could just simply use the 95% confidence level, which is what I'm going to use here. So I know I'm going to be looking in this column here. Now, if you have a look with the T tables, I also need the degrees of freedom. Now, degrees of freedom are really easy to calculate. Okay, so let's actually calculate them here now. So just remember that the degrees of freedom is always going to be equal to n minus 1. So my sample size in this case is 25, so therefore my degrees of freedom is going to be 1 less than that. It's going to be n minus 1, so 24. So if I come here, and if I look for 24 degrees of freedom, or as close as possible to it, I know I'm going to be looking in that row. So I've got the column, I've got the row, let's just find the intersection point then. So that's going to be 2.064. So 2.064 units of standard deviation above and below the mean will include 95% of the data which I'm after. Okay, so 2.064 is my t-value, okay? Next, I need to calculate what my standard error is going to be. So my standard error in this case is going to be my S, my standard deviation, which is 4, divided by the square root of my sample size, which is 25. Okay, so square root of that, sorry. Okay, so let's stick that into a calculator. So I get 2.064 times by, well, it's effectively 4/5, isn't it? Which is 0.8. So times that by 4/5. That's going to be 1.6512, okay? So actually, I'm just going to say 6.15, that's fine, okay? So in other words, that's how much to add and subtract to my sample mean in order to include 95% of my data. So therefore, if I actually construct my confidence interval, I have x bar, which I've got as 100, minus my margin of error, which I've just calculated as 1.65, that's my lower threshold. And my upper threshold should be 100 plus 1.65. So let's have a look at that, shall we? So in other words, my confidence interval for my true population mean should be 98.35, and my upper value should be 101.65. So just a reminder what this confidence interval is literally saying. So that's my final answer. What my confidence interval is literally saying is that in order to include 95% of my data, okay, I'm saying that I can be 95% confident that based on this sample data, my true population mean weight of my chocolate bars should lie somewhere between 98.35 grams and 101.65 grams. Of course, I could increase that confidence level, but it would mean that I'd end up with a wider interval where my population mean could lie between. I could also decrease that confidence interval, but it would mean that I'll also decrease my confidence level as well. So it's a bit of a kind of playoff, okay? So at the moment, I'm 95% confident based on this sample data that my true population mean weight of my chocolate bars should lie somewhere between 98-ish grams and 101-ish grams, okay? Okay, so question 3 then. Question 3 is still a confidence interval question, but it's now using 2 sets of sample data, and I'm using those to compare them against each other. So I have 2 competing bakeries, and they each claim that they bake the longest baguettes in town. So baguette is a type of bread, a French bread, okay? To test this claim, the town mayor buys 40 baguettes from bakery A and finds that the mean length of these 40 baguettes is 63 centimetres. So let's actually have a look at this. So I'm going to write down the data as I come across it. So bakery A, okay, I have a sample size of 40, okay, because he buys 40 baguettes, or they buy 40 baguettes. I find that the mean length of those 40 baguettes is 63 centimetres. And of course that's sample mean, because I'm talking about the mean of the 40 baguettes. In other words, the sample of 40, okay? So the sample mean is 63. And again, the standard deviation of those 40 baguettes, the standard deviation of the 40 baguettes, that sample standard deviation, that's equal to 4 centimetres, okay? If I go for bakery B, okay, so the other set of data that I've got, they buy 50 baguettes. Okay, so n is 50, it's a slightly bigger sample for bakery B, and they find the mean length, and again it's of the 50 baguettes, therefore it's sample mean, that's 67, and the standard deviation, again of the 50 baguettes, that's sample standard deviation, is equal to 7. Okay, fantastic. So now we need to construct a 90% confidence interval, symmetric, for the difference in the population mean lengths from each bakery. Okay, so first of all, let's figure out what type of distribution we're going to be using here. So I'm going to bring up my little question, sort of which I need to ask myself. So because this one is talking about 2, I need to make sure that these questions are satisfied for both. Okay, so actually I can sort of alter this slightly and say, well, rather than asking is n greater than or equal to 30, because I'm trying to compare 2 samples against each other, I need this for both of n1 and n2. In other words, both samples have to have a sample size greater than or equal to 30. And likewise, when I come down here, when I say, do I know the population standard deviation, I need to know the population standard deviation for both. So I need to know it for both population 1 and sample 1 and sample 2. Okay, so I need to know it for both. Okay, so let's have a look. So right, do we know that n is greater than or equal to 30 for both? So let's ask the first question. Do I know both n1 and n2 is both greater than or equal to 30? So in fact, I'm going to number these. This is going to be n1 and n2. This is going to be x bar 1 and x bar 2. This is going to be s1 and s2, just to make it a little bit easier and clearer with the notation. So okay, do I know that n is greater than or equal to 30 for both? Well, yes, I do. Both sample sizes are bigger than or equal to 30. Okay, so I've got a tick there. Okay. However, do I know the population standard deviation for both of them? Well, no, I don't. I only know the sample standard deviation. So therefore, in this case, I know that I'm going to be using the t distribution. So because I'm going to be using the t distribution, I need to calculate the degrees of freedom. So degrees of freedom, the way which I calculate it, is slightly different for 2 samples, okay? Because it's not just n minus 1, okay? It's basically going to be n1 minus 1 added to n2 minus 1. So in other words, it's the degrees of freedom for both of these samples added together. Or if you prefer, you can write that as n1 plus n2 minus 2. Okay, so the degrees of freedom in this case, well, n1 is equal to 40, n2 is equal to 50, that's 90, take away 2, that's going to be 88. So I've got 88 degrees of freedom there. Now, as a general rule of thumb, the bigger the degrees of freedom, remember degrees of freedom tells you the number of things that are free to change, okay? So in this case, it's always n minus 1 because the idea is you need to know... If you know everything up until 1 less, then you know everything, then things are allowed to change, okay? And I have kind of explained that during the lecture as well, so feel free to go back and look at degrees of freedom in a little bit more detail there. But effectively, it's the number of things that are free to change, okay? So in this case, 88 things, 88 in this case baguettes are free to change until I know everything about the situation. Okay, so fine. Let's actually do this. So I need to calculate a difference in the population means confidence interval. In other words, I'm saying, well, look, if I take away mu1 from mu2, in other words, the population mean weight of baguettes made by bakery A, take away the population mean weight of bakery B, I need to work out what is the confidence interval going on here, okay? Well, that's nice and easy. It follows a very similar setup to what we were doing in the last questions, okay? So it's just going to be the difference in the sample mean weights, okay? So sample means, but difference in the sample means, okay? Take away some margin of error. And the upper bound is going to be difference in sample means again, but add on some margin of error. Now the margin of error is going to be ever so slightly different to before, okay? So this is where you need to be careful. So it's still going to be using, well in this case, t distribution. I still need to look at how many units of standard deviation will include, well in this case 90% of my data because I'm asking for a 90% confidence interval, okay? So I'm still going to be looking for that. However, I'm going to multiply it by the standard error. Now the standard error of 2 samples put together, or the 2 random variables put together, and again we proved this in one of the lectures, okay, is equal to, well in this case I only know S1 and S2, so it's not going to be sigma, but it's going to be S1 squared over N1 plus S2 squared over N2. And again, if you're interested in where that came from, we derived that in the lecture for this theme. Okay, So let's go ahead and calculate it. So first of all, I know 88 degrees of freedom, and I'm looking for a 90% confidence interval. So let's jump back to our tables. Let's get rid of the last question. Okay, so I'm looking at a 90% confidence interval, or a 5% upper tail probability, because of course 10% is split over 2 tails, so 5% each, okay? And I'm looking for 88 degrees of freedom. Now you notice in this case that there isn't 88 in the tables. That's fine, okay? The idea is that obviously as the degrees of freedom increase, the t distribution looks remarkably like the z distribution anyway. Hence the reason why you see down here that for anything greater than or equal to 1,000, they're just like, hey, just use the z distribution, come on. Okay, so that's fine. Okay, so we need to look for 88. So I'm going to be looking at 80 because that's the closest value in my tables. Of course, the differences between 80 and 1,000 and 100 is kind of negligible, especially when you consider sort of degrees of freedom lower. So in other words, what I'm trying to say there is that if you're looking at low degrees of freedom, the differences for values between like 1 and 2 degrees of freedom will be far greater than the differences between, say, 80 and 100 degrees of freedom. Okay, so just be aware that for lower degrees of freedom, there's going to be bigger differences in the units of standard deviation you're using at than if you're looking at higher units of degrees of freedom. That's the reason why the kind of resolution of degrees of freedom sort of drops off and it goes to sort of every 10 or every 20 eventually. So let's have a look. 80, that's the one I'm looking for. That's the closest value. All right, fine. So I'm looking at the intersection point. So I'm looking at about 1.664 units of standard deviation each side of the mean in order to include 90% of my data. Okay, so 1.664 is the magic value. So 1.664. And then I'm going to calculate, well, okay, S1 squared is going to be 4 squared over N1, which is 40. Added to S2 squared, which is 7 squared, over N2, which is 50. So I'm just going to stick all of that in your calculator. Let's see what we get. So I get there 1.95. Okay, so M is equal to the margin of error, thing which I add on and subtract each side, is 1.95. Okay, so I'm just going to make this a little bit smaller, just so I've got a little bit more room to actually construct my confidence interval down here. So let's do this. So I need difference in the sample mean. So difference in the sample means, remember, the order matters. I'm doing x1 bar take away x2 bar. Sample mean of bakery A take away the sample mean of bakery B. So it's going to be 63 take away 67. That's going to be -4, and I need to take away M, which is 1.95. So that -4, remember, came from x bar 1 take away x bar 2. In other words, it comes from 63 take away 67. So the order matters here. Okay, so less than or equal to mu1 take away mu2. Less than or equal to, okay, so x1 bar take away x2 bar, I've just done that, it's -4, but this time I'm going to add on my margin of error, which is 1.95, just calculated that. Okay, so let's do this. So -4 take away 1.95, that gives me a -5.95. So that's my lower threshold, -5.95. Less than or equal to, well, the difference in the true population means should be anything from -5.95 up until, well, okay, what's -4 plus 1.95? So -4 plus 1.95, that should be equal to -2.05. So that there is the confidence interval for the difference in the true population means. So next question then, what does this confidence interval show? Well, just remember, because I'm looking at a difference in the difference in the sample in population means, excuse me. So because I'm looking for a difference in the population means, I can actually interpret what's going on here. Remember, the original question was asking for a difference in the mean lengths baked by the two bakeries, because each bakery thought they baked the longest baguette in town. So you go out, you collect sample data from each bakery, and you suggest, whether there is actually a difference between them. So let's have a look. I'm doing a confidence interval for mu1 take away mu2. In other words, bakery A take away bakery B. Okay, so I'm looking for a difference between bakery 1 and bakery 2. Okay, now if this is greater than 0, so have a look at this. Okay, what I'm basically saying is that mu1 take away mu2, the difference in the mean baguette length baked by each bakery, that's negative. Okay, because look, the lower threshold is -5.95, the upper threshold is -2.05. 0.05. That there has got to be negative. Okay, so I'm basically saying at 90% confident that the difference in the true population mean lengths of these two baguettes baked by each bakery has got to be negative, because I've got a negative value on my lower threshold and a negative value on my upper threshold. So therefore, it's got to be negative. You know, the difference in the mean lengths has also got to be negative as well. Okay, so because it's negative, I'm going to write that as less than 0. Okay, now what that basically implies, if I just do a little bit of rearranging, is that mu1 has got to be less than mu2. I just simply add mu2 to both sides. So what that simply means is that the mean length of baguettes baked by bakery 1, mu1, is less than the mean length of baguettes baked by bakery 2, so mu2. Okay, so I'm literally saying here that the baguettes baked by bakery, well, okay, mu1 is bakery A, okay, is less, oh sorry, is let's say is shorter, okay. Okay, so the baguettes baked by bakery A is shorter than the baguettes baked by bakery B. Okay, now this is really important, the next part, okay, at the 90% confidence level. Okay, so you need to state how confident you are in that claim. Obviously, if that confidence level is really, really small, then you can kind of infer, well, hang on a minute, I don't actually believe what you're saying here. If that confidence level is much higher, then obviously there's much more confidence in your statement, okay? But you must put the confidence level there, so then people can actually infer what you mean there, okay? They can actually infer for themselves, as long as they understand what confidence levels means, of course, okay? But that's basically what you interpret, okay? You realise that because your confidence level, or sorry, your confidence interval has got to be negative. Your lower threshold is negative, your upper threshold is negative, therefore, your overall threshold has got to be negative as well. In other words, mu1 take away mu2 has got to be negative. Do a bit of rearranging, therefore you can make the inference that mu1 has got to be less than mu2. Clearly, if the lower threshold is positive and the upper threshold is positive, then your mu1 take away mu2 is also got to be positive, which means that mu1 has got to be greater than mu2. Okay, in other words, bakery A is baking longer baguettes than bakery B. If one is negative, if your lower threshold is negative, your upper threshold is positive, then it means it kind of spans 0. So you can kind of say it's roughly equal to 0. So therefore you can say they're actually equal to each other. Okay. So those are the three different cases you can have. In this case, lower threshold is negative, upper threshold is negative. Therefore the difference in the two baguettes have also got to be negative, which means that you can infer at the 90% confidence level that bakery A bakes shorter baguettes than bakery B. Okay. Okay, so let's have a look through question 4 then. So we've got the heights of sweet pea plants grown in a nursery are known to be normally distributed with a standard deviation of 0.1 metres. The nursery owner claims that the average height of their sweet pea plants is 1.8 metres, and a sample of 50 plants are analysed and found to have a mean height of 1.75 metres. Test at the 10% level of significance whether there is evidence to suggest that the nursery owner is correct. So, okay, this is a hypothesis testing question. How do I know that? Well, a couple of things. Number one, we're given that we've got a level of significance, okay? So there's a level of significance now rather than a confidence level. So it's not a confidence interval question, okay? But also you see the word that we've got here, test, okay? That tells me that I've got a hypothesis and I need to work out what those hypotheses are. And I've also got a level of significance, therefore it's hypothesis testing, not confidence intervals. Now sure, confidence intervals are incredibly useful and we can infer some information about it, and often in real world statistics, when you see hypothesis testing, you'll often see confidence intervals alongside those. But for these types of questions, I just want you to go through the testing procedure for hypothesis testing. I'm not worried about you giving you confidence intervals as well, okay? Now you notice first of all, there's a lot of text going on here. So what I'm going to do is I'm just going to go through, underline the key bits of information that I need, write those down, so sort of extract them, and then let's see where we're at, okay? So let's go through it sequentially. So we've got the heights of sweet pea plants, and we know they're normally distributed with a standard deviation of 0.1. Now, that 0.1 metres, that standard deviation of 0.1 metres, it's not talking about any sample that we've collected. Okay, it's just simply saying the heights of the sweet pea plants are normally distributed and here's their standard deviation. Therefore, we can adequately assume that that 0.1 meters refers to population standard deviation. We're not talking about standard deviation of a sample, we're talking about the population standard deviation. So let's write that down. So sigma equals 0.1. Now the nursery owner makes a claim that the average height of their sweet pea plants is 1.8 meters. So let's actually write that down. That's their claim that they're making. That's their null hypothesis. So I'm going to write down H0 for null hypothesis is that the height of their sweet pea plants, or the average height of their sweet pea plants, is 1.8 meters. So I'm talking about a population average height there, so mu, and that's equal to 1.8 meters. Okay. Now, we need some sample data in order to test this claim. So we go out, we collect 50 plants, so I write down n equals 50 as my sample size of my sample. That's analysed, and we find that the average height of our sample is 1.75 meters. So I write down x bar equals 1.75. All right, fantastic. So this here is our sample data, okay? So we've got sample mean, 1.75, sample size of 50, and we can use the population standard deviation of 0.1, okay? So what else do I need then? This is the information I've got. Oh, actually, there's one more bit of information. It's the level of significance. So I'll write that down over here. The alpha is our level of significance, and it's 10%. Okay, so what other information do I need? Well, look, I've got my null hypothesis. I now need my alternative hypothesis to work out what type of test I'm going to be doing. So left-tailed, right-tailed, or two-tailed. So let's think. I need to find evidence to suggest that the nursery owner is correct. So they're either correct or they're incorrect. I'm not interested in whether the mean height is greater than 1.8 or less than 1.8. I'm just saying, is the nursery owner actually correct? Is it equal to 1.8 or is it not equal to 1.8? So that's my alternative hypothesis. So my alternative hypothesis is simply saying, is it not equal to 1.8 meters? So is it equal to 1.8 meters or is it not equal to 1.8 meters? Okay, I think this is enough then to work out or to go through the test procedure, okay? So first things first, I need to work out, is it a t distribution I'm going to be sampling from or a z distribution? So let's do that now over here. So I'll bring up my few questions that I need to ask. So remember, there's only two questions. Now, one is about sample size, the second is about population standard deviation. So in this case, is my sample size bigger than or equal to 30? Well, let's have a look. I have 50 sweet pea plants in my sample. So yes, it is, okay? Yes, my sample size is bigger than or equal to 30. Next question, do I know what my population standard deviation is? Yes, I do, okay? I got the 0.1, I didn't have to find that from my sample that I collected, okay? So therefore I know my population standard deviation, so therefore I can get away with using my Z distribution. Remember that the questions which I ask, if the answer to any of those questions is no, it's a T distribution, otherwise it's a Z distribution, so they both answered yes. All right, fine, let's go through this then. So now I'm going to be using a Z distribution. Let's now work out what type of test I'm going to be using. And I can use my alternative hypothesis to figure that out, okay? So you notice in this case that I'm interested in my alternative hypothesis. I'm interested that my mean weight, my population mean weight, is not equal to 1.8 meters. That means it could be greater than or it could be less than, okay? So it's a two-tailed test. It's both greater than or less than, okay? So it's a two-tailed test. Now, clearly, if I was looking at strictly less than, it would be a left-tailed test, okay? Or if it was strictly greater than, it would be a right-tailed test. But in this case, not equal to is both less than and greater than, okay? That's not equal to, so it's a two-tailed test. So what I'm going to do is I'm going to draw out my normal curve. So I'll draw my normal curve over here, okay? And I'm going to put my hypothesized mean in the middle. So at the moment, I'm supposing, okay, my null hypothesis, let's suppose that that is correct, okay? Now what's the probability of getting this sample here? So a sample mean of 1.75 from a sample size of 50, given that I know the population standard deviation is 0.1, okay? So okay, I need to first of all work out the critical values, the cutoff points of my two tails. Because I'm basically saying I'm interested in it not being equal to 1.8, which means it could be either less than, so I'm looking for values which lie down here, or greater than, okay, so values which lie up here instead. So I need to work out what's the cutoff point, okay? How many units of standard deviation each side of the hypothesized population mean would I need to be, so further than that, in order to say, no, do you know what? The chance of getting this sample up here is significantly low, therefore I can reject the null hypothesis. So what are my critical values? What are these cutoff points which I've drawn in here? Now, just for consistency, I'm going to change that 1.8 to 0 because the critical values are going to be given in terms of units of standard deviation from the hypothesized mean, okay? So I'm going to put that to 0, okay? Then it'll be easier to see. So let's figure it out. Well, look, I've been given that the significance level is 10%, which means that the total area of these two critical regions, so this region down here and this region up here, the total area is 10%. In other words, I should, by pure chance, reject 10% of all of my data. Okay. Now clearly I'm separating it over two separate regions. It makes sense because I want the size of these two critical regions to be the same, so there's the same chance of being less than the hypothesis size mean as there is being greater than. I want the size of these two critical regions to be the same. So in other words, I'm going to split this 10% significance level equally among the two regions. In other words, each region is worth 5% of my data. Okay, so each region is 5% of my data. Now, I know that I'm using the Z distribution. I figured that out from before. So now I can go to my Z tables and work out how many units of standard deviation I need to be from the hypothesized mean in order to allow 5% of my data into the critical region, each side. Okay, so I'm going to come to my tables. Here we go, and I'll clear that off from a previous question, and I'll come to my Z table. So here's my first Z table, and I'm looking in here for 5%, or as close as possible to 5%. Now remember, 5% is 0.0500, okay, because it's given as a decimal. So I can go in here and I can hunt around and I find that it's in here. So 0.05 is sort of halfway between there. So I know that I'm going to be looking about negative 0.645. So I can either use negative 1.64 or negative 1.65, or I could use negative 1.645. But I'm actually going to show you a slightly quicker way of pulling this data out. So rather than having to hunt in all these sort of thousands of numbers to try and find a value which is close to 0.05, okay, I'm going to show you an alternative method. Now you remember that the t-tables, so I'm going to come down to the t-tables here, you remember that the t-tables are basically an approximation of the z-tables, okay? The idea is that if you have a small sample size, the t-curve is ever so slightly flatter than the z-curve, okay? We learned that in the central limit theorem, okay? The idea is you increase the sample size, the distribution becomes more peaked, okay? And the t-distribution helps us to get a more accurate representation of data, of like the distribution of our data when we have a smaller sample size. But what that means is that as I increase the sample size, and of course the sample size is given by, it can be determined by degrees of freedom, because it's just sample size minus 1. So as I increase the sample size, the t-distribution should approach the z-distribution anyway. And if you have a look down here, for example, okay, we've actually only got things up to about 1,000 sample size. And if you look at the bottom row of our table, you might just be able to see it if I zoom in, okay, the bottom row of our table actually has z, okay? In other words, what you're saying is that if you have a sample size which is more than 1,000, you're better off using the z table anyway, okay? Now I can exploit that here, because remember that I'm using a tail probability of 5%. In other words, if I use this 5% here, okay, of course that means that I'm using a confidence level of 90%, okay, because it's 5% on each tail, okay, then that means that I should just be able to read it off nice and neatly from here. Now the reason why I prefer to do it using this method, so 1.645, you remember, is exactly the same value as I got using the z-table. So I could use the z-tables if I want. But the reason why I prefer using the t-tables is because it's easier to find, okay? The way the t-tables works is different from the z-tables. Remember that the z-tables, the probabilities are in here, which means you've got thousands of probabilities to hunt from, and then you have your units of standard deviation given by the rows and the columns of these tables. Whereas the t-tables work in the opposite way. The probabilities, in this case the tail probabilities, are given by the rows, okay, so the top and the bottom, okay? And then the units of standard deviation are given in here, which means that if I know I'm hunting for a specific probability, like 10% or 5% or 2.5% or 1%, I can easily just read it off along the top of my t-tables. And I know that the bottom row of my t-tables are effectively just z-tables anyway, okay? So it's slightly quicker, I think, to use it this method. Anyway, long story short, the units of standard deviation from the hypothesized mean, which would give me 5% of my data being rejected each side, is going to be 1.645, okay? So let's write that in. So those are my critical values. I have 1.645 up here, and I have negative 1.645 down here, okay? So in other words, if I end up with my data, my sample data, lying more than 1.645 units of standard deviation from my hypothesized mean, then I know I can reject the null hypothesis. I know there's a very low chance of that happening, so therefore I can reject the null hypothesis. But let's actually calculate, let's actually find out how many units of standard deviation my sample data lies from my hypothesized mean, okay? So let's actually calculate my test statistic now. So test stat for short, okay? Well, I know that I'm going to be using the Z distribution, okay? So I can write Z equals. So Z equals. Okay, now the formula, or the way which I calculate it, is first of all, I take my sample mean, which is my 1.75. That's found in my sample data. And I need to find the difference between that and my hypothesized mean. Remember that I'm assuming that that hypothesized mean, the 1.8, is true. Okay, the 1.8 meters is true. So I'm going to find the difference between my sample mean and my hypothesized mean. Now I'm going to divide it by the standard error. Okay, I'm not going to just divide by the 0.1. The reason being is because the size of my sample is 50. Okay, so therefore it should be the case that 0.1 should decrease by 50. Now, there is an argument each way here. You could say that you could use 0.1 because you know that my sigma, you know that my 0.1 is my population standard deviation. Okay, so I know that my population should be 0.1 anyway. Okay, if you wanted to divide by the square root of 50 to argue it from that perspective, that is fine, okay, and you wouldn't get it marked wrong, okay, but in this case, I am actually just going to divide by 0.1 on the basis that that 0.1 has come from a population measure rather from the sample data measure, okay, so I don't have to apply the central limit theorem there, I can just divide by 0.1, okay. Okay, fine, so let's actually stick that in a calculator and see what we get out. So I find that that comes out as negative 0.5. In other words, my sample data here lies 0.5 units of standard deviation from the true population mean. Now, just a point about that, if you're still kind of hung up on the fact, you say, no, you should always divide by the square root of n. Well, in this case, it's because this value here, this 0.1, hasn't come from sample data, okay? It's come from true population level data, okay? So I don't have to apply the central limit theorem there. Okay, but like I say, if in an exam question this came up, it's a point which is important, but it's not a point which I'm going to knock marks off. Okay, so if you decide to divide by the square root of 50, I wouldn't have marked you wrong. Okay, so okay, I get 0.5, negative 0.5. Well, look, negative 0.5 lies in here. Okay, so in other words, it doesn't lie in my critical region. It doesn't lie in my critical region. So therefore, I know that because my test statistic doesn't lie in my critical region, it means that I'm well within the allowance which I'm allowing. I'm allowing 90% of my data to be allowed before I say that something's not right here. Okay? So because negative 0.5 doesn't lie in my critical region, I'm not going to reject the null hypothesis. I'm going to fail to reject the null hypothesis. Okay? But just to be complete, I'm also going to give a p-value here. I'm also going to give the probability of obtaining this sample data if that null hypothesis is true, just to give some extra evidence. So remember, for a p-value, it's always the probability of obtaining this sample, okay, so this sample here, or a more extreme sample. So let me explain why I'm saying that. Remember that my tables are cumulative. In other words, they're adding together all of the different possible values that you can have up until that value. Okay, so less than or equal to, in other words. inputs. So it's not just one particular value. It's not just the probability of obtaining this sample. It's the probability of obtaining this sample, but also like less than or equal to that sample. Okay, so 1.75 or less, so 1.74, 1.73, or 1.72. Okay. In other words, a more extreme sample would mean a sample that lies further away from the hypothesized mean. Well, look, the hypothesized mean is in here. Okay, the hypothesized mean is this line here. It's where I put the 0. Okay, so more extreme would basically mean further away from that. In this case, towards the left. Okay, so my p-value I will find by going into my z tables, because remember I'm using my z distribution here, and I'm looking for a value which lies further to the left of negative 0.5. Okay, so let's come into my tables then. Let's find my tables, and I'm going to be using my Z tables, and I'm looking for negative 0.5, so I'll get rid of my previous answer here, and I'm looking for negative 0.5, which is going to be that one there, because that's negative 0.50, okay? So it's 0.3085, all right, so 0.3085 is my p-value, okay? Now if I wanted that as a probability, that's about 31%, so 30.85% there. That's my p-value. So remember, the p-value is the probability of obtaining this sample if my null hypothesis is true, or a more extreme sample. In other words, a sample which lies further to the left of that. The reason why I have to include the or more extreme is because my p-values are, my tables are cumulative. Okay, so these tables here are all cumulative. They're all less than or equal to probability. So when I looked this value up, it's not the probability that it's equal to negative 0.5. It's the probability that z is less than or equal to negative 0.3085. Okay, so sorry, negative 0.5. So that's the reason why I say or a more extreme sample. It's not just this value. Okay, so now I think we're in a position where we can actually put it all together and we can come up with a decent conclusion. Okay, so my conclusion, people kind of freak out about putting conclusions of hypothesis tests, but I'm going to give you a 4-step recipe which you just follow and it should be straightforward. So number one, I'm going to give it in terms of the test statistic. Okay, so the test statistic. Now, first of all, I'm going to actually state what my test statistic is. So my test statistic I found to be negative 0.5. Now, of course, if you found a different test statistic because you chose to divide by the square root of n, that's fine, okay? It's not going to get marked wrong, okay? Because it kind of shows the correct method, okay? But strictly speaking, it should be 0.5 or negative 0.5. So I got my test statistic was equal to negative 0.5. Now I need to relate this in terms of, I need to relate this or compare this to my critical values, okay? So my critical values was, well, I found that as 1.645 or negative 1.645. Well, I'm going to give the critical value which it's closer to, okay? So it has to be between negative 1.645 or 1.645, so I'm going to give the critical value as negative 1.645 on the basis that that's the critical value which is closest to it, okay? So I'm going to give critical value as negative 1.65. That's the first thing I need to state. Second thing I need to state is my p-value, okay? So my p-value I found to be 30.85%, okay, so 30.85%. And I'm going to compare that in relation to my significance level, okay, so my significance level was given as, well, my significance level was 10%, but I'm going to relate that to the 5% level which I'm looking at, because of course there's a 5% chance of falling into each region, okay, so I'm going to relate that to 5%, okay, but either way it doesn't matter. Third thing I'm going to state is, do I reject the null hypothesis or do I fail to reject the null hypothesis? Well, actually no, before I do that, I need to state what these things mean, okay? So I need to say that the test statistic, which was negative 0.5, well, that was clearly greater than my critical value, so it wasn't in the critical region. Next, I need to do it in terms of the p-value. Well, the p-value was also greater than my significance level, so therefore it wasn't in the critical region. So therefore I can state now, do I reject the null hypothesis or fail to reject the null hypothesis? Well, clearly in this case, I fail to reject the null hypothesis. Okay, so I'll write that down. So I fail to reject the null hypothesis. Now remember, I can either reject null hypothesis or fail to reject the null hypothesis. I can't say accept at all. Never say accept in hypothesis testing. It's either reject or fail to reject. Also notice that we've done everything assuming the null hypothesis is true. So therefore I need to say, what do I do with my null hypothesis? Not my alternative hypothesis. I need to do another test to kind of figure out what's happening with the alternative hypothesis. Okay? So I failed to reject the null hypothesis. Then the fourth step is to actually state what this means in the context of the question. So remember, the question was talking about the heights of sweet pea plants, okay? So I said that I'm taking sweet pea plants at random, okay? And I think that the height of these sweet pea plants, the average height of the sweet pea plants, is 1.8 meters. So using my evidence, using my data, okay, I failed to reject that null hypothesis. In other words, I have said that there is not enough evidence to suggest that the null hypothesis, sorry, that's the height of the sweet pea plants, that's my null hypothesis, the height of sweet pea plants is anything other than 1.8 meters at the 10% level of significance, okay? Okay, so hopefully that makes sense. Now there's a few little nuances which you need to do here. With the conclusion, always compare the test statistics to the critical value, okay? So say, is it in the critical region or not? Then compare the p-value to the significance level. Now, the reason why I've used the significance level over 2, okay, is because I've got a two-tailed test, okay? And that's the only reason why I've used 5% instead of 10%. Okay, because I know that the total value of my critical region is 10%, so the left and the right put together. But in this case, because I'm only using the critical value, the p-value in relation to one of my critical regions, okay, does it lie in one of the critical regions? I'm using 5%, which I'm comparing it to. Okay, so hopefully that makes sense. Okay, so let's have a look through question 5 then. So question 5 is about a clinical trial that's undertaken to test whether an injection for reducing blood pressure is effective or not. So a group of 75 participants who have similarly high blood pressure are recruited. 35 of these participants are randomly assigned to a control group and are not given the injection, whereas 40 participants are randomly assigned to a treatment group and are given the injection. So in other words, you collect together 75 participants. They all fit the criteria of this trial in the sense they have to have similarly high blood pressure. And basically 2 groups are created, one that's given the injection to see whether there's been an effect, and one who's not given the infection. These are kind of the control group. These are the people who say, well, look, if you did nothing, this is what you expect during this time, whereas the 40 participants who are given the injection kind of sees whether there's been an improvement or perhaps a poorer performance instead. At the end of the trial, the blood pressure of each participant is taken. The mean blood pressure of the control group is given by 45. Now, I don't know what the units are of the blood pressure, but it's 45. And the standard deviation of the control group, so in other words, the 35 participants that have been randomly assigned, is 3. And we're also given the same statistics for the treatment group, which is 36 as the mean and 5 as the standard deviation. Test at the 5% level of significance where there's enough evidence to suggest a significant difference in the blood pressures of the 2 groups. Okay, so let's write down the information so that we don't have to keep referring to this big paragraph each time. So group 1, in fact, I'm not going to call them group 1, I'm going to call them the control group, because these are the people that are not given the injection, perhaps they're given a placebo instead. Okay, and then we've got the treatment group. All right, fine. So these are the 2 groups. Now, how many people are given the control? Well, there's 35 participants. So I'm going to go N1 equals 35. And there were 40 participants in the treatment group. Okay, so that'll be N2. And that's the data which is given there. Okay, we've got the mean of the control group is 45. And the standard deviation is given as 3, and the mean of the treatment group is 36, and the standard deviation is 5. Okay, cool. Now we've been told to test at the 5% level of significance. So 5%, that's our level of significance, so alpha equals 5%. Whether there is enough evidence to suggest a difference in the blood pressures of the 2 groups. Okay, so here's where we need to be careful about what the alternative and what the current hypothesis is. So the null hypothesis is to say that these 2 groups have no difference, okay? So they're equal to each other. So in other words, the mean blood pressure at the population level, if everybody in the population was given this, who had high blood pressure, was given this treatment, okay, there'd be no difference between them. So mu1 is equal to mu2, okay? So there's no difference between having the injection and not having the injection. Whereas the alternative hypothesis means that we have to suggest a significant difference in the blood pressures. Now, there's two ways that you can look at this. You can either say that the people in the treatment group have a lower blood pressure than the people in the control group. Okay, the idea is you're given this medication, and the hope is that the blood pressure in the treatment group will go down. That would suggest a difference. However, it could also be that this treatment has a negative effect as well. Okay, so you could say that mu1 is greater than mu2. In other words, the people in the control group end up at the end of the trial with a blood pressure which is higher than that of the treatment group, the people that receive this treatment. Okay. However, you've also got to take into account that there could be a negative effect as a result of this treatment as well. In other words, the blood pressures go up. Okay, there's not enough detail there to determine exactly what you want. Okay. So all I'm going to do is I'm just going to say it's not equal to. Okay, I don't know whether it goes up, I don't know whether it goes down. Now, as it happens, you can actually infer as an alternative hypothesis from your sample means, okay? So it looks as if just purely looking at the sample means, the treatment is having a positive effect. Those people that are given the treatment, their blood pressures tend to go down, okay? So in actual fact, you could get away with saying that the people in group 1 have a higher blood pressure than the people in group 2. However, I'm going to play it safe and I'm going to use a two-tailed test. I'm just going to say, is there a difference? Okay, so just be careful about that. All right, fine. So let's work this out. From here, I know that because it's not equal to it could be greater than, it could be less than, I'm going to say it's a two-tailed test. Okay, which means that when I draw my curve in, so here's my normal curve like so, at the moment I'm hypothesizing that these two treatment groups, the treatment and the control group rather, they have the same blood pressures. Okay, so that's my current hypothesis, that's in the middle. Okay, and basically it's two-tailed, so I want to say, well, what's the probability that there's a difference over here, or what's the probability that you end up over here? So based on this sample data, what's the probability that end up into either of these two regions? So I need to work out the critical value. Before I do so, however, I need to work out, is it a T distribution or is it a Z distribution? So let's work that out now. Remember, there's two questions you need to ask yourself. Number one, is N1 and N2 greater than or equal to 30? In other words, is the sample sizes big enough for both the treatment and the control group? Okay. The second question you need to ask yourself is, do you know the population standard deviation for both groups? Okay, so not just one, do you know the population standard deviation for both? Okay. Now just remember, if the answer to that question is yes, and the answer to that question is yes, in other words, you know that both of these things are true, okay, therefore you can get away with using the Z distribution. If the answer to either of those questions is no, you have to use the T distribution. Okay, so if the answer to the question of is the sample size big enough is no, use the T distribution. Do you know population standard deviation for both of them? If the answer to that question is no, use the T distribution as well. So let's have a look. Well, first of all, have we got big enough sample sizes? Yes, we have, 35 and 40. So the answer to the first question is yes. Oops, the answer to the first question is yes. But do we know the population standard deviation of both? No, we don't. Okay, this is a treatment. Okay, so we're using samples. The only information we've got is about the 35 participants and the 40 participants. Okay, this is a brand new treatment. It's never been tested before. So even if we did know the population blood pressure of the people who are not given the injection, like that's reasonable. We could know that. We wouldn't know the population standard deviation of the people that are given the treatment. Okay, because it's brand new. It's never been tested, so we don't know what that population standard deviation should be. So the answer to that question is no, therefore we have to use a T distribution, okay? So first of all, we need to work out what's the degrees of freedom. So the degrees of freedom should be equal to, just remember it's same formula as last time, it's N1 plus N2 take away 2. So it's 35 plus 40 take away 2. I'm just using the N1 and N2. So that's going to be equal to, well, it's going to be equal to 73, okay? So 73 is the degrees of freedom. Okay, so it's quite high, it's okay. All right, fine. So let's go about actually calculating this. First of all, I need to find the critical values. Okay, I need to find the number of standard deviations each side of the difference in the sample means, or the hypothesized difference in the population means, where we can cut off and say this is now a significant statistic. Okay. So what I'm going to do is I'm going to jump over to my t-tables. Remember, I'm using 73 degrees of freedom, and remembering that my alpha is 5%, well, okay, let's look at my tails then. So because I'm looking at 5% significance level, that gets split over my two tails, so 2.5% up here and 2.5% down here. Okay, so I'm going to use 73 degrees of freedom, and I'm looking for a tail probability of 2.5%. Okay, so let's have a look at that. So here's my t-tables. Let's get rid of the last question. Okay, fine. And I'm using 73 degrees of freedom. Well, I'm just going to find the closest one, which in this case is 80. Okay, and I'm looking for confidence level. Well, my confidence level has got to be 95%. Okay, or my tail probability, which is 2.5%. Either way, I'm looking in that column. So I find that the number of standard deviations each side of the mean, which include 90% of my data, and it rejects it 5% at the time, should be 1.99. That's my critical value. Okay. So my critical values are 1.99 up here and negative 1.99 down here. So in other words, when I calculate the difference in my sample means, if those sample means, that sample data lies further than 1.99 units of standard deviation from the mean, from the hypothesized difference in the means rather, so hypothesized difference in the means, then I know that I can reject the null hypothesis. So let's have a look at that. Okay, so let's actually write down the formula for calculating my test statistic. So I'll do my test statistic down here. Okay, so my test statistic, which in this case is t, of course, okay, is going to be given as, well, first of all, it's going to be given as x1 bar take away x2 bar. Okay, so difference in the sample means. And then I'm going to take it away from the hypothesized difference in the population means. And then I need to divide that by my, well, effectively, I need to divide that by my standard error, okay? I mean, there's different sort of words for it. You can use pooled standard deviation if you like. I'm just simply going to use the square root of, S1 squared, so 3 squared, over N1, which is 35, plus S2 squared, which is 5 squared, over N2, which is 40. Okay, so that's fine, to be honest with you, as your standard error. Okay, pooled standard deviation, whatever you want to call it. So let's calculate this. So x1 bar take away x2 bar, that's going to be 45 take away 36, that's going to be 9. Now, what's my hypothesized difference in my population means? What's my mu1 take away mu2? Well, I can use that from my null hypothesis. So if mu1 is equal to mu2, that means the difference between mu1 and mu2 should be equal to 0. Okay, so that thing there should be equal to 0. So if I stick all of this into my calculator, let's see what I get. So I get 9.58. Now, before I go any further, that should start majorly ringing alarm bells. Because what I'm basically saying is that the difference in my sample data, so I've got my control data, my data for my control group, data for my treatment group, I'm basically saying that this sample data lies 9.58 units of standard deviation away from my hypothesized difference in my means, which of course at the moment is 0, okay? So my hypothesis is saying there's no difference, okay? But actually I'm ending up with a test statistic of 9.58. Well, given that pretty much every single value, certainly on a Z curve and also for a T curve to a certain extent as well, should lie within about 3.5 units of standard deviation each side of the hypothesized difference in the means. 9.58 units of standard deviations is well beyond the 3.5 kind of units of standard deviation on my curve. So therefore, if I think about a p-value, okay, I can actually just infer a p-value here. If you think about my p-value, well, my p-value is kind of way out over here on the right-hand side. Okay, it's way out here, certainly well above my cutoff value, my critical value of 1.99. So therefore, as I move further away from the hypothesized difference in the means, the value, the probability should become 0. Okay, so I'm saying that my probability, I don't say that my p-value is equal to 0. I say that my p-value is less than, let's say, 0.1%, so 0.001. Okay, you never say it's equal to 0 because of course it's not equal to 0. It's just really, really small. Okay, it's close enough to 0 that you can consider it as 0, but it's not equal to 0. Okay, so I'll just say it's less than 0.1%. Okay, now the final little thing I need to put is a little conclusion. Okay, so here we go. Here's my conclusion. So what are the things I need to state? Well, first of all, I need to state my test statistic is. So my test statistic is 9.58, which lies way out over here, well into the critical region. Okay, so first of all, my test statistic of 9.58 lies beyond the critical value, so I'll just write crit val for short, of 1.99. Okay. Next thing I'm going to put is my p-value. Okay, so my p-value of, in this case, less than 1%, so 0.1%, all right, is below the significance level, so alpha, of 5%. Okay, so therefore we reject the null hypothesis. Okay, so there is enough evidence based on our sample data, so enough evidence to suggest a difference between the control group and treatment group, and I should say their blood pressures. So control groups and treatment groups' blood pressures. Okay. Now in this case, our sample data suggests that there is a decrease. Okay, so it goes from 45 for the control group to 36 for the treatment group. Okay, so there is a difference. It's suggesting it is going down, which is the right direction. Okay, the pharmaceutical company will be pleased, or whoever put this drug together, this treatment together. But based on our evidence, we basically got a test statistic of 9.58, which is huge. 9.58 units of standard deviation from the hypothesized difference in the means. It's well beyond the critical value of 1.99. Remember how I got the p-value? I said, well, look, I don't even need to look in the tables. I know that all the values in the table lie between about 3.5 units of standard deviation each side the mean. So if I'm looking at a unit of standard deviation about 9.58, more or less 10 units of standard deviation from the hypothesized difference in the means, that is basically zero, okay? The probability of getting that value is so small. Doesn't mean it's zero, so it could still technically happen, but it's so small that it means there's probably something wrong. So the thing which is likely to be wrong is our null hypothesis, so therefore we reject the null hypothesis. There's enough evidence to suggest a difference between the control groups and the treatment groups' blood pressures. Okay, if you put that, you'll get all full 10 marks. Okay, so let's have a look through the final question then, to question 6. So we're told that 80 randomly chosen people are asked to estimate a time interval of 60 seconds without using a watch or clock. We're given that the mean of these 80 estimates is 58.9 seconds, and we're also told that previous evidence has shown that population standard deviation of these kind of evidence is 5 seconds. Test at the 5% level of significance where there is evidence to suggest that people tend to underestimate the time interval. All right, fine. So let's go through first of all, and let's just write down what we've got. It's a hypothesis testing question. So let's write down our sample data and let's write down things like significance levels. Okay. So first of all, we're told that 80 randomly chosen people. So that's our sample size. 80 randomly chosen people asked to estimate a time interval of 60 seconds without using a watch or clock. Okay, fine. I'm not going to write down anything to do with the 60. That's just information about what they are doing. Okay, it's not an actual statistic. Now we're told that the mean of the 80 estimates is 58.9 seconds. So in other words, X bar is 58.9 seconds. Okay, and we're also told that previous evidence, so not this sample data, but previous evidence instead has shown the population standard deviation is 5 seconds. So we're given sigma, okay, we're given that's equal to 5, okay. We're then asked to test at the 5% level of significance, so alpha in other words is 5%, whether there is evidence to suggest that people tend to underestimate the time interval, okay, so that'll become important in just a second. So first of all, we're going to write down our null and alternative hypothesis. So first of all, we are saying that the mean of these 80 people, okay, so the mu, the population mean, we're assuming that everybody can calculate or count to 60 seconds without using a watch or clock, okay? So we're basically assuming that everybody can do it properly, okay? So the mean should be 60, okay? So it's a bit of a weird one, the null hypothesis, okay? But we need to test whether people tend to underestimate the time interval. Well, the null hypothesis is basically saying, let's assume everybody can calculate the time interval correctly, or count the time interval correctly. So let's assume that mu is equal to 60. Whereas the underestimating the time interval bit, so this bit down here, basically means, is there evidence based on this particular sample data, okay, so here's our sample data, is there evidence to suggest that actually the mean is less than that? Okay, so actually people tend to underestimate, in other words, count less than 60 seconds, okay? Now, from this, I know, from my alternative hypothesis, I know then that because mu is less than 60, because it's a less than, so I'm asking for the population mean being less than some value, I know it's a one-tailed test, and because it's less than, it's a left-tailed test, okay? In other words, when I draw my curve out, so here's my normal curve here, okay? Here's my normal curve. At the moment, I'm assuming the null hypothesis to be correct. So I'm assuming that 60 is the correct thing in the middle, okay? And I'm looking for a left-tailed test. So I'm looking for what's the probability that actually people end up over here, okay? So it's strictly speaking left-tailed. It's not two tails, it's just one tail because mu is less than 60. Now, what's the size of that critical region? Well, it's 5%, okay? That's our level of significance. So it's 5% there. All right, fine. So first things first, I need to work out, am I using a t-distribution or am I using a z-distribution? So let's go over here, okay? First of all, I need to ask the question, have I got a sample size which is greater than or equal to 30? In this case, yes, I have. I've got 80 people in my sample. That's more than big enough to kind of satisfy that condition there, okay? Obviously, if it wasn't, I would use the t-distribution, okay? Next question I need to ask is, do I know what the true population standard deviation is, okay? Well, in this case, yes, I do, okay? I'm told that using previous evidence, okay, so nothing to do with the sample data, previous evidence shows that the population standard deviation is 5. So the answer to that question is yes. The answer to the n being greater than or equal to 30 is also yes. Both questions answer correctly, answer yes. Therefore, I know I'm going to be using the z distribution. But of course, if I didn't know that, it would be the t distribution. So always just check, first of all, am I using z or am I using t? Okay, so it's a z distribution in this case. So let's go ahead and actually calculate what our critical value is. In other words, how many units of standard deviation below the hypothesized mean do I need to be in order for there to be a suggestion that it's unlikely for this to happen? Okay, so first of all, I need to go into my tables and I need to find the tail probabilities being 5%. So what's the probability that I end up less than 5%? Well, fortunately, okay, if I come to my Z tables, I'm looking for 5%, so 0.05. So let's clear that. So 0.05 is what I'm looking for, or as close to as possible to it. So 0.05, well, it's halfway between those two, so it's going to be about negative 1.645, okay? But of course, if you're happy, you could have also used the t-distributions, which may be slightly quicker, okay? So remember, I'm looking for a tail probability of 5%. If I use the last row in my table, that will give me my z probability. So I'm looking for this column here, so that's going to be 1.645, okay? So 1.645 is my value. All right, fine. Oops, let's find the right place. There we go, okay? So in other words, negative 1.645 is my critical value. Anything below 1.645 units of standard deviation from the mean, okay, so I convert that back to 0 to say that that's where my hypothesized mean is. That's going to be a suggestion that there's not enough evidence to suggest that that null hypothesis is correct. Okay, so let's have a look at this. Let's calculate now my test statistic. Let's work out how many units of standard deviation does my sample lie below this hypothesized mean. Okay, so to calculate my test statistic, I'm just going to go z is equal to my sample mean, which is 58.9, take away my hypothesized mean, which is 60, divided by, well, okay, divided by, in this case, I need to divide by my standard error, okay? So that's going to be 5 over the root of 80. Like so. So if I stick all of that into a calculator, let's see what we get. So I get myself negative 1.97. So, in other words, my test statistic is 1.97. So my sample lies 1.97 units of standard deviation below my hypothesized mean. Okay, so on my graph, it lies here. So here's my test statistic, negative 1.97. So in other words, it lies within that critical region. So therefore, there's evidence to suggest that I can reject the null hypothesis. In other words, people do tend to underestimate the 60-second time interval. But just to be sure, I'm also going to calculate the p-value as well, okay, just to be complete. So to calculate the p-value, I'm looking for the probability of obtaining a value more extreme than this sample. In other words, I'm looking for a value which lies to negative 1.97 or less, so further than negative 1.97 units of standard deviation from the hypothesized mean. That's more extreme. It's further towards the critical region, okay, or further inside the critical region. It wouldn't be this way. The reason being is because that's moving towards the hypothesized mean. I want to be moving away from the hypothesized mean, okay? So therefore, I want to find the probability on my Z tables that I end up with a value less than negative 1.97. So let's go and quickly look that up. Okay, so let's look on my Z tables, and I'm looking for 1.97 below, or negative 1.97 and below. Let's have a look in here. So negative 1.9 is here, 0.07 is here, find the intersection point, 0.0244. Okay, so that's my p-value, 0.0244. Or if you prefer, that's about 2.5%, 2.44%, okay? So the only thing left to go then, I've got my test statistic, I've got my p-value, I'm now in a position where I can actually write down my conclusion. So I'm going to do it over here where I've got a little bit more space. So remember, the first thing I need to state is test statistic, okay? So I can say my test statistic of negative 1.97 is further into the critical region, okay? Or I could just say less than, to be honest with you, is less than my critical value of, well, my critical value was negative 1.645. Okay, so negative 1.645. That's the first statement. Okay, so in other words, my test statistic lies further away from the hypothesized population mean than my critical value. In other words, my cutoff value is negative 1.645. My test statistic is negative 1.97. It lies further away from the hypothesized mean, okay, in terms of standard deviations. The other thing I need to say in terms of my p-value. So my p-value is equal to 2.44%, which is less than my significance level, which remember was 5%. Okay, so in other words, I said, well, okay, an acceptable, so 5% or above, if I end up with a probability of obtaining this sample, which is 5% or above, that means that I can kind of fail to reject my null hypothesis. But if it's less than 5%, that means the probability is suitably low enough to suggest that the probability of obtaining this sample is low, so therefore it's unlikely that null hypothesis is correct. So therefore, what's the conclusion? Well, the test statistic is lower than my critical value, the p-value is lower than my significance level, therefore I reject the null hypothesis. Okay, so I reject the null hypothesis. The last thing I need to state is what that means. What does rejecting the null hypothesis mean in the context of the question? Well, just remember, in the context of the question, I'm talking about people estimating a 60-second time interval without a watch or clock or any kind of timing means, okay? So therefore, I can say there is evidence from my sample data at the 5% level of significance to suggest that people underestimate a 60-second time interval. Okay, so words to that effect is fine. So just remember, the way you do a conclusion, people always get kind of worked up about the conclusion. It's not that hard. Do it in 4 stages. Number 1, test statistic related to the critical value. Number 2, p-value related to the level of significance. Number 3, do you reject the null hypothesis or fail to reject the null hypothesis? Number 4, what does that mean in the context of the question? Okay, so if you reject the null hypothesis, what does that mean with regards to, in this case, the calculating the time interval? Okay, if you fail to reject the null hypothesis, it would be saying that you that people are able to estimate a 60-second time interval perfectly fine, or at least the sample data doesn't suggest anything alternative. But in this case, it's rejecting the null hypothesis, which means there's evidence to suggest at the 5% level of significance using our sample data that people are unable to test to calculate a 60-second time interval without a timing clock. In fact, they tend to underestimate it. Okay, so just remember, it's nice and simple. Just break it down. Okay, first of all, find your sample data. Okay, so that's there. Write down your hypotheses, okay? Work out what type of test you need to do. So is it left-tailed, right-tailed, or two-tailed? Then work out what distribution you're using. Find your critical values. Find your test statistic. Find your p-value. Then do your conclusion. Okay, so your conclusion is nice and straightforward. It's really straightforward. It's a nice, simple procedure, but just make sure you get it right, okay?